but there you have it. So what did we learn from here? Is this how is this transmitted genetically? Dominant, recessive, sex-linked, autosomal. This disease. X recessive, so sex-linked, X recessive. Yes, is that right? Because why? What was a big clue on this? When you look at it, you can tell?
Because it was on the male.
Because only the males are getting it, if you look at that. And it's recessive because
The females are passing it on?
not necessarily, that's why it's X-linked. But it's recessive because a different way. They say the same thing, yeah. There are carriers, right? The females are carriers, therefore the females are passing it on, but that's the key, right? That's what you meant, right? All right, so one of these, again, I just picked a couple of these at random from your homework. So this is dwarfism, okay? In this case, what we want to focus on is the achondroplastic dwarfism. Okay, the achondroplastic dwarfism is the one that we want to look at because it has a autosomal dominant inheritance pattern. All right. Now, having said that, there's a bit of a disclaimer. In 7/8 of the time, it's actually a spontaneous mutation that causes achondroplastic dwarfism. Okay, it's only 1/8 of the time where it's an autosomal dominant inherited disorder. But there's not much to talk about in this class about the spontaneous mutation because this isn't really a genetics class. This is just a brief overview. So we'll look at that 1/8 of the time where it's autosomal dominant. Okay. So as you would expect, what does achondroplasia mean? What's achondroplasia mean? Without cartilage, right? A without chondral cartilage. And plasia is growth, like we saw before with, the dysplasia and metaplasia and hyperplasia, right? So this is without cartilage growth. And if you look back to your Bio 201 days when you were studying bones, right, you know that you have to have some cartilage before it can ossify and turn into hard bone. Okay? So, achondroplastic dwarfism. If you look at the picture of these guys up here, you're going to see that their heads, these twin boys, their heads are the same size. Their trunks are the same size. The only difference is those long bones, right? The arms and the legs where you're going to need a lot of that cartilage to make the long bones, those are shorter. Okay? There's no deficiencies in mental capacity or anything like that. But as you'd expect, the short limbs are going to throw off the physics of the limbs. So you end up with some limb deformities occasionally, not always, but occasionally. Okay. There is this primordial dwarfism. That's an autosomal recessive thing. We're not really focusing on that. I don't think that made your list in your homework, but it could have. It's just, again, another example of an autosomal recessive disease. Has anybody ever seen primordial dwarfism? Like on TV or in person?
In person.
No way.
Yeah, I did.
I've never met anybody who's seen somebody in person with that. Is there a story there, or is it? Hey, what's up?
His parents were normal. He was just, it was so long ago, I was younger, but it was so abnormal that I was like, weird.
Huh, okay. I have a picture of that, I think, on another slide here, but again, not a whole lot to say, I guess, at this point about that. Here's your, again, achondroplasia. This is also a good example of the age of the father. You really don't see that very often. Yeah, the age of the mother does tend to make a difference on whether or not, you have any kind of birth defects, birth genetic mutations, that sort of thing. For example, like Down syndrome, right? Does anybody remember like the magic number, or know the magic number on how old a female is before
35.
you start really increasing the odds of Downs?
35.
Yeah, 35, right? So I don't remember the exact number, but if you're like 20, the odds of you having a child with Down syndrome is like 1 in 2,500 or something like that, right? And then that if you were to graph it, it kind of goes up very slowly until you hit about 35 and then start shooting up like crazy, right? And that's, I think, why we're seeing a lot more kids with Downs nowadays, just because, there's a lot more change in society where you're seeing a lot more career, as evidenced by you guys, right? And, putting off having children until you're a little older, and then right about the time you hit 35, it starts really dropping or increasing the odds of having a child with Downs. But anyway, that's not what I'm talking about. What I'm talking about here is the other example that you just don't see very often, where it matters how old the father is. Okay? In this case, that does cause some new mutations as the father gets older. And I mean older, not, I know you guys think I'm ancient, but like 20 years older than me, kind of older. Okay, then you start seeing that. Because again, the sperm's made, I think, millions of them every single day. So there really has to be, you have to kind of be in that old age category before you really start seeing these kind of mutations happening. Okay. All right, here's our pedigree-ish thing, cartoon/pedigree of achondroplasia. Really don't have anything to add to that. As you can see, again, just like with our Punnett squares, you have a dominant trait in there somewhere, you're still going to have some odds. In this case, like this is kind of the one that we drew on that very first slide with the Punnett squares, right? You had each parent had a dominant trait, but there was still 1/4 every time they have a child, 1/4 chance or 25% chance that they would have a child that did not have dwarfism. And you can see from this picture that they did actually have a couple of children without dwarfism at all. Okay. Did they have any kids that died?
Yeah, but don't do the smart things.
Yeah, I really don't know if they did or not. Has anybody ever seen this show?
I went to their farm, actually.
What?
Yeah.
Okay.
We would go and get our pumpkins there. So.
They have a pumpkin farm?
Yeah.
Oh, cool.
They're from
And
Hillsboro, so.
did you happen to ask while you were picking up your pumpkin if any of your children ever died?
Nope.
Didn't think so.
I didn't.
Don't know. Does anybody happen? I don't know. Okay. Here's a primordial dwarfism again. She's about 6 years old right there, by the way. I think her name's Kennedy. She's about 6 years old in that picture. And she's, I don't know, about this tall. Right? At first, when I saw it, and by the way, there's a video link. You could watch it. It's kind of cool. It takes like 20 minutes, though, so we're not going to. But if you look at her real close, you can see she has like this overbite. And I thought at first maybe that was part of the syndrome, but if you watch the video, you'll see where they're actually putting her to bed. Again, she's 6 years old, she's that big, but they're putting her to bed like with a binky every night. Still. I'm like, well, okay, if you do that to any 6-year-old all the way through until they're 6 and keep them binky, they're going to have a horrible overbite. So I think that's probably not related to the syndrome. I'm not convinced that guy up in the upper right here either, because for some reason that reminds me of Boba Fett, where he like cloned himself, because that's the exact same face on that dude, just a little version. So I don't know, that might not be primordial dwarfism.
So is she mentally delayed?
You know, Has anybody ever seen the series with Kennedy?
I've seen it, but I forgot about what happened there.
I never saw the series. Based on that one 20-minute video clip, she kind of looked like she was a little bit mentally delayed, but it was really, you know, again, it was like a 20-minute video clip, so I really couldn't say. It's not like they interviewed her. As far as I know, she doesn't even talk, but, you know, again, it was a video clip, and I have no idea. I can't believe nobody's seen that show. Man, how times change. I'm telling you, just a year ago, everyone was like, yeah, I've seen that show. You know, 2 years ago, like 100% of the people seen the show. But. All right, times are changing too fast. Okay. How about this one? Has anyone ever seen polycystic kidney disease? You have? Not outside the body, yeah, but good story.
My dad has it and I have it.
What's that?
My dad has it and I have it.
Oh, you're kidding. So your dad has it and you have it?
And my sister.
And your sister?
I have one sister that didn't get it.
So this would be transmitted genetically. How? If that many people have it? Probably dominant, yes? Again, it's an autosomal dominant, if you notice. It is hitting both sexes, right? So what do you do about that?
Blood pressure medicine, diet, ensure diet,
Okay.
diuretic sometimes. My dad's on the transplant list and he's on dialysis.
Your dad's on the transplant list?
Yep.
And he has had dialysis?
He's on dialysis right now.
Okay. Does that mean his kidneys are really, really cystic right now then?
Yes. The kidney function, I think, is at 17% now.
17%. Ouch. So that's definitely a stage 5 kidney failure out of 5. Well, I'm first sorry to hear that. What about these signs and symptoms? Does that seem pretty
Pretty accurate.
pretty accurate? Okay, why would you get the hypertension, by the way? Not you, anybody else? Why would you get hypertension with polycystic kidneys? Because what?
Because of the small arteries inside your kidneys that control a lot of our blood pressure. You have these cysts pushing on them to increase the pressure.
Okay, yeah, as you can see, if you have that many cysts, it probably is messing with, you know, the filter, the glomerulus, the arterioles, the capillary system, right? And just things aren't getting through like they should be. And of course, what is it, 22 to 25% of our blood that comes out of the heart goes to the kidneys. And yeah, that would make a big difference in blood pressure right there. What would be another danger? This is a kind of a thought. If you had polycystic kidneys, hypertension because of that, what would be another danger of any other organs in the body?
Your heart.
Your heart, right? Because chronic high blood pressure, assuming it wasn't being treated, right? Chronic high blood pressure could lead to what kind of heart issue that we talked about before, huh? Yeah, hypertrophy, right? Could have a hypertrophic left side of the heart. So it can lead to a lot more issues. Obviously, the rest of that stuff, the back pain, the kidney infections, that sort of stuff makes sense probably, right? Because I mean, it's a mass. It's a bunch of little masses making a bigger mass, right? And of course, you can kind of expect anytime, again, untreated high blood pressure, we're assuming, right? Could also lead to those aneurysms, whether in the brain or
Can it eventually move to different organs, the polycystic
kidneys.
tumors?
As far as I know, it does not. Yeah,
It
it is.
It's interesting because they call it polycystic kidney disease, but the cysts are actually on the liver as well as the pancreas and ovaries and everything.
See, I did not know that.
And supposedly it doesn't affect the function of those organs.
So the cysts go pancreas, ovaries, liver,
Everything in there.
but doesn't affect those. Wow. All right, good to know. I did not know that. So, question for you, since you know better than anybody. If your dad gets his transplant, gets new kidneys, is this going to cause future kidneys to become cystic or not?
You know, I don't know the answer.
That's a good
That's a good question. I'm not sure, and it doesn't seem like we would consider it because he's not a very good candidate, to receive a transplant. So it doesn't seem like an option for him.
He's not a good candidate?
Candidate.
Oh, well, that's unfortunate. Okay. All right. I'm gonna move on. This is just depressing me. Okay. All right. So obviously these are gross specimens and an MRI of someone with polycystic kidneys. Fairly easy to identify if they get that large, of course.
Wow.
Okay, as you can see, they can get really, really, really big. Okay, sickle cell anemia. Transmitted, autosomal recessive, right? So would you expect to see this a lot or just a little bit in
Well,
society?
In certain areas and certain racial groups. Like African.
Okay, again, as a general rule, you don't see a lot of recessive diseases, except this one does have a unique qualifier where you see it a lot. Okay, especially in certain areas, and that qualifier is what? Why do you see sickle cell anemia a lot more than other recessive diseases or recessive traits? You guys have probably seen this before, right? Dial 202
Yes.
usually goes over sickle cell. So what's the big thing? Why do you see it so often? Yeah.
It's resistant to malaria.
Because like that little thing says in the lower right, it's resistance to malaria, right? So malaria transmitted by mosquitoes can attach to regular, normal red blood cells. Okay? It can't attach to the sickle red blood cells, but the sickle red blood cells, even though they're not as efficient and they do have their issues, they do still carry oxygen, right? So if you have a sickle, or if you have a malaria outbreak, and if you can imagine like this little village in the middle of nowhere with not really a lot of healthcare, a whole lot of people get sick. And the ones without sickle cell anemia, I have a higher chance of dying. They don't make it through the malaria outbreak. On the other hand, those ones with some round blood cells and some sickle cells, yeah, they're going to get sick, but they're probably going to live through it, right? So then they live long enough to reproduce, because they're literally the last man and woman standing kind of thing. And that's why you see this, even though it's an autosomal recessive, you see it a lot more often. Does anybody know anyone with sickle cell? One person here? Wow, two? Usually see a lot more than that. Again, don't tell me any names or anything, but if your person that you know with sickle cell, are they very sick or not sick or somewhere in the middle?
She's really sick, but she gets blood transfusions like I think every month. or
Wow.
something like that, because she has it bad.
Okay. Sorry to hear that. It's like all bad news today, right? What about you? Did you raise your hand?
She gets sick. I know
Sometimes it's worse than others.
Sometimes worse than others, sick?
Like sometimes she's in the hospital.
Oh, sometimes hospital,
Yeah.
okay. So she has these episodes? Okay. Sickle cell, again, the reason I bring that up is because sickle cell is one of those conditions where it's on a huge, huge spectrum, okay? Sometimes you have people that are very sick and they're constantly having these crises, you know, where they're having blood issues and possibly blood clots and or, you know, it gets so bad, you know, the anemia that, you know, they have to have blood transfusions and that sort of thing. On the other hand, I've actually seen people who had sickle cell that were on scholarships for the GCU track team, okay? Obviously, not affecting them very much, although technically they had it. I have a very good friend who used to be a fighter pilot. He had sickle cell. They grounded him for a while, but then they realized, after he fought them, that he'd been flying for 10 years already in a fighter jet and it never affected him before. And so they were like, oh, I guess you're okay. And they put him back in the cockpit and he ended up becoming like a wing commander. So, yeah, sickle cell is one of those things where it's on a huge spectrum of how severe the disease is. And again, some places, you might not even want to call it a disease, right? Because it's actually protective. But you still end up with the autosomal recessive genetic pattern. A lot of times they can treat it by giving on the very last line. Again, normally I said we don't really talk about treatment that much in this class. It's not really the point of it, but sometimes we'll see something like this that the treatment is unusual. So it's probably worth remembering. In this case, hydroxyurea. Okay, hydroxyurea, we give that to somebody and it actually stimulates the growth of fetal hemoglobin. Okay, you guys remember your blood? Where a normal hemoglobin strands are hemoglobin A, you have 2 of those, hemoglobin B, you have 2 of those, right? And that's what's normally in your red blood cells. Okay, in sickle cell, you're having hemoglobin S, or sickle. So it's different, and that's what's kind of twisting and making that odd shape of the red blood cell. So it doesn't change that, but if you give somebody hydroxyurea and it produces fetal hemoglobin, then what was the big thing with fetal hemoglobin? What was the big advantage of it? Yeah, it really, really pulls oxygen to it, right? It has a very high affinity for oxygen. Of course it has to, because that's the only way the fetus is getting oxygen is through that umbilical cord and that blood, where they're stealing the oxygen off from the mother. Okay, so this is one way to help the patient with sickle cell deal with the issues associated with low oxygen. Okay. Not going to do a ton to stop the clotting, as far as, you know, those sickled cells not wanting to go through those small arterioles and capillaries very well. Okay. And here's yet another